To determine the extent of concern with available fault current, several factors must be considered. Circuit protection coordination is crucial. The primary function of protective devices is to ensure that the fault current is interrupted before it causes damage. Coordination between the fuses and circuit breakers is essential to ensure that the correct device operates first, clearing the fault and protecting downstream equipment. The continuous current rating and maximum fault current rating, interrupting capacity of all circuit protection devices and equipment must be higher than the available fault current at their location. This includes fuses, circuit breakers, contactors, transformers, and other equipment that may be exposed to fault current. According to the National Electrical Code, the available fault current should not exceed the interrupting capacity of any overcurrent protective device, fuse, or circuit breaker in the circuit. National Electrical Code Table 110.9 provides guidance on the maximum available fault current for different voltage systems. The evaluation process consists of multiple steps. Firstly, determine the available fault current at the distribution panel. Calculate or obtain the maximum fault current that could occur at the distribution panel using the utility's data or performing fault current calculations. Secondly, check circuit breaker ratings. Compare the maximum available fault current to the interrupting capacity of the circuit breakers in the distribution panel. Ensure that the circuit breakers have an interrupting capacity higher than the available fault current. Thirdly, consider downstream equipment. Analyze the distribution system downstream of the distribution panel. Identify any molded case circuit breakers or other protective devices that may be exposed to fault currents higher than their ratings. Fourthly, evaluate equipment ratings. Check the continuous current ratings and interrupting capacities of transformers, contactors, and other equipment that may be affected by the available fault current. Fifthly, implement mitigation measures. If necessary, upgrade protective devices or implement other mitigation measures to ensure that all equipment is adequately protected against the available fault current. Based on the information provided, the interrupting capacity of the molded case circuit breakers in the distribution panel and any downstream protective devices should be checked to ensure they are rated higher than the available fault current of 22,000 amps. Also, consider the equipment ratings and implement any necessary mitigation measures to ensure the safety and reliability of the system. Fault current calculations are essential for electrical system design and safety. Available fault current refers to the maximum current that can flow in a circuit under fault conditions, such as a short circuit. Understanding and mitigating potential fault currents is crucial to protect equipment, prevent fires, and ensure personnel safety. Here is a breakdown of the key aspects of fault current calculations. Fault current calculations are performed to determine the magnitude of fault current at various points in an electrical system. This information is used to select appropriate overcurrent protection devices, such as circuit breakers and fuses, with adequate interrupting ratings. The interrupting rating of a protective device must be greater than the available fault current at its location to safely clear a fault. There are two primary methods for calculating fault current, the point-to-point method and the impedance method. The point-to-point method is a simplified approach suitable for smaller systems with relatively short conductor runs. The impedance method, also known as the per-unit method, is more accurate and suitable for larger, more complex systems. Firstly, you need to gather system data. This includes utility source impedance, transformer impedance, conductor impedance, and motor contributions. Utility source impedance is typically provided by the utility company and represents the impedance of the power source feeding the system. Transformer impedance is usually expressed as a percentage and can be found on the transformer nameplate. Conductor impedance depends on the conductor size, material, length, and installation method. Motor contributions refer to the additional fault current supplied by motors connected to the system during a fault. Secondly, calculating fault current using the point-to-point method. You start at the source, typically the utility transformer, and calculate the fault current at each point in the system. Calculate the transformer secondary fault current using the formula I fault equals transformer kilovolt amps times 1000 divided by the square root of 3 times the secondary voltage, all divided by the transformer impedance in percent divided by 100. Calculate the conductor impedance using impedance tables provided in the National Electrical Code or from conductor manufacturers. Adjust the conductor impedance for temperature if necessary. Calculate the fault current at the end of the conductor run using the formula I fault at the end of the conductor equals the transformer secondary fault current divided by 1 plus the transformer secondary fault current times the conductor impedance. Repeat the calculations for each point in the system where the fault current needs to be determined. Thirdly, calculate fault current using the impedance method. Convert all system impedances to a common base, typically 1000 kV amps. Calculate the per unit impedance of each component such as transformers, conductors, and motors using the formula Z per unit equals Z actual divided by Z base, where Z base equals kilovolt squared divided by megavolt amps base. Calculate the total per unit impedance of the system by summing the per unit impedances of all components in the fault current path. Calculate the fault current in per unit using the formula I fault per unit equals 1 divided by Z total per unit. Convert the per unit fault current to actual amps using the formula I fault equals I fault per unit times I base, where I base equals kilovolt amps base divided by the square root of 3 times kilovolts. Motor contribution must also be considered. Motors connected to the system can contribute to the fault current during a fault. The motor contribution is typically estimated as a multiple of the motor's full load current, usually ranging from 1 to 6 times the full load current. Include the motor contribution in the fault current calculations by adding it to the fault current calculated from the utility source and transformer. Software tools are available to simplify fault current calculations, especially for large and complex systems. These tools automate the calculation process and provide detailed reports of fault current levels at various points in the system. Common software tools include SKM Power Tools, EasyPower, and ETAP. Once the fault current calculations are complete, compare the calculated fault current levels to the interrupting ratings of the overcurrent protection devices. Ensure that the interrupting ratings of all circuit breakers and fuses are greater than the available fault current at their location. If the calculated fault current exceeds the interrupting rating of any protective device, mitigation measures must be implemented. Firstly, consider upgrading overcurrent protection devices. Replace circuit breakers and fuses with higher interrupting ratings to accommodate the available fault current. Secondly, current limiting devices can also be installed. Current limiting fuses and circuit breakers can reduce the magnitude of fault current and protect downstream equipment. Thirdly, impedance can be added. Adding impedance, such as reactors or impedance transformers, in the fault current path can reduce the fault current levels. Fourthly, system reconfiguration can also be done. Reconfiguring the electrical system, such as by splitting buses or using multiple smaller transformers, can reduce fault current levels. Regular updates of fault current studies should be performed. Fault current studies should be updated periodically, especially after any changes to the electrical system, such as the addition of new equipment or modifications to the power source. Regular updates ensure that the overcurrent protection devices remain adequate and that the system is protected against potential fault currents. It is important to consult with a qualified electrical engineer when performing fault current calculations and implementing mitigation measures. Fault current calculations are complex and require a thorough understanding of electrical system design and protection principles. An experienced engineer can accurately assess the fault current levels and recommend appropriate solutions to ensure the safety and reliability of the electrical system. Fault current calculations are a critical aspect of electrical system design and safety. By accurately calculating fault current levels and implementing appropriate mitigation measures, you can protect equipment, prevent fires, and ensure the safety of personnel. Remember to consider all relevant factors such as utility source impedance, transformer impedance, conductor impedance, and motor contributions, and to consult with a qualified electrical engineer for assistance. Considering the specific scenario, The utility is upgrading a 400 amp 600 volt 3-phase 3-wire delta system to a 600/347 volt 3-phase 4-wire system. The new system will have a fault current of approximately 22,000 amps at the transformer bushings. The existing main fusible switch has fuses rated at 300,000 amps interrupting rating, which is adequate. However, the molded case circuit breakers in the distribution panel and any downstream protective devices must be checked to ensure they are rated higher than the available fault current. Follow these steps. Firstly, gather information on all circuit breakers and protective devices in the distribution panel and downstream. This includes the manufacturer, model number, and interrupting rating. Secondly, compare the interrupting ratings of the circuit breakers and protective devices to the available fault current of 22,000 amps. Ensure that all devices have an interrupting rating greater than 22,000 amps. Thirdly, if any circuit breakers or protective devices have an interrupting rating less than 22,000 amps, they must be replaced with devices with a higher interrupting rating, or other mitigation measures must be implemented. Fourthly, consider the equipment ratings of transformers, contactors, and other equipment that may be affected by the available fault current. Ensure that these devices are also adequately protected. Fifthly, implement any necessary mitigation measures, such as current limiting fuses or circuit breakers to reduce the fault current levels. Sixthly, document all calculations and findings in a fault current study report. This report should include the system data, calculation methods, results, and recommendations. Based on this evaluation, the appropriate steps can be taken to ensure the safety and reliability of the electrical system. The key is to ensure that all overcurrent protection devices have adequate interrupting ratings and that equipment is protected against the available fault current. Regularly review and update the fault current study to account for any changes to the electrical system. The process of upgrading an electrical service from a 3-wire delta system to a 4-wire system involves several important considerations. A delta system typically consists of 3-phase conductors without a neutral, while a 4-wire system includes 3-phase conductors and a neutral conductor. The addition of a neutral conductor provides a grounded reference point and allows for the supply of both phase-to-phase and phase-to-neutral voltages. When upgrading from a delta to a 4-wire system, it is important to ensure that the new system is properly grounded. Grounding provides a low impedance path for fault currents to return to the source, which helps to protect equipment and prevent electrical shock hazards. The grounding system should comply with the requirements of the National Electrical Code. The neutral conductor should be properly sized to carry out the expected neutral current. The neutral current can be caused by unbalanced loads, harmonic currents, and other factors. The neutral conductor should be sized based on the requirements of the National Electrical Code, which takes into account the expected neutral current and the potential for harmonic currents. The new transformers being installed should be compatible with the existing equipment and loads. The transformers should have the appropriate voltage ratings, kilovolt amp ratings, and impedance. It is also important to consider the transformer's ability to handle harmonic currents. The conductors connecting the new transformers to the existing equipment should be properly sized to carry the expected load current. The conductor size should be based on the requirements of the National Electrical Code, which takes into account the conductor's ampacity, voltage drop, and temperature rating. Overcurrent protection devices, such as circuit breakers and fuses, should be properly sized to protect the conductors and equipment. The overcurrent protection devices should have an interrupting rating that is greater than the available fault current at their location. The overcurrent protection devices should also be coordinated to ensure that the correct device operates first in the event of a fault. Surge protection devices should be installed to protect the equipment from voltage surges caused by lightning, switching, and other factors. Surge protection devices should be installed at the service entrance and at any sensitive equipment. The electrical system should be properly labeled to identify the different circuits and equipment. The labeling should comply with the requirements of the National Electrical Code. All work should be performed by qualified electrical contractors who are familiar with the requirements of the National Electrical Code. The electrical contractor should obtain all necessary permits and inspections. The upgrade from a Delta to a full wire system should be thoroughly documented. The documentation should include drawings, specifications, and test results. The documentation should be retained for future reference. Load calculation should be performed to determine the total load on the electrical system. The load calculation should take into account the existing loads and any new loads that will be added. The load calculation should be used to size the new transformers, conductors, and overcurrent protection devices. A power quality analysis should be performed to identify any power quality problems such as harmonic currents, voltage sags, and voltage swells. The power quality analysis should be used to develop solutions to mitigate any power quality problems. An energy efficiency analysis should be performed to identify opportunities to improve the energy efficiency of the electrical system. The energy efficiency analysis should be used to develop solutions to reduce energy consumption. Safety is a top priority when upgrading an electrical system. All work should be performed in accordance with the requirements of the National Electrical Code and other applicable safety standards. Workers should wear appropriate personal protective equipment such as safety glasses, gloves, and hearing protection. Lockout-tagout procedures should be followed to energize equipment before working on it. A thorough commissioning process should be performed to verify that the new system is operating properly. The commissioning process should include testing all circuits and equipment to ensure that their functioning is designed. The commissioning process should also include training the facility personnel on the operation and maintenance of the new system. Maintenance is essential to ensure the long-term reliability of the electrical system. A preventive maintenance program should be developed to inspect and test the electrical system on a regular basis. The preventive maintenance program should include cleaning equipment, tightening connections, and replacing worn parts. The upgrade from a Delta to a full wire system is a complex project that requires careful planning and execution. By following these guidelines, you can ensure that the upgrade is performed safely and reliably. The utility's decision to install a new pole with 3 transformers and extend the secondary wiring to the top of the pole is a common practice for upgrading electrical services. This approach allows the utility to provide a more reliable and efficient power supply to the customer. The installation of the 4th, neutral, conductor is essential for providing a grounded reference point and allowing for the supply of both phase-to-phase and phase-to-neutral voltages. The utility's decision to install 300 kV transformers is based on the load calculations for the customer's facility. The transformer size should be adequate to supply the existing loads and any future loads that may be added. The utility's indication that the fault currents on the new system will be slightly higher than the existing system is due to the lower impedance of the new transformers. Fault current level is an important factor to consider when selecting overcurrent protection devices. The main fusible switch with fuses rated at 300,000 amps interrupting rating is adequate for the new system. However, it is important to check the interrupting ratings of the molded case circuit breakers in the distribution panel on any downstream protective devices to ensure that they are greater than the available fault current. The molded case circuit breakers in the distribution panel are typically used to protect branch circuits. The interrupting rating of these circuit breakers should be greater than the available fault current at their location. If the interrupting rating of any of the circuit breakers is less than the available fault current, the circuit breaker should be replaced with circuit breakers with a higher interrupting rating. The motor control center for the compressor equipment has all high rupturing capacity fusing internally. High rupturing capacity fuses are designed to interrupt high fault currents. The interrupting rating of the high rupturing capacity fuses should be greater than the available fault current at their location. The available fault current at the transformer bushings is 22,000 amps. This is the maximum fault current that could occur at the transformer bushings. The fault current will decrease as it travels through the conductors and equipment in the electrical system. The fault current at the distribution panel will be less than 22,000 amps. The fault current at the branch circuits will be even less. It is important to calculate the fault current at each point in the electrical system to ensure that the overcurrent protection devices are properly sized. There are several software programs available that can be used to calculate fault currents. These software programs take into account the impedance of the conductors, transformers, and other equipment in the electrical system. The results of the fault current calculations can be used to select overcurrent protection devices with the appropriate interrupting ratings. In addition to checking the interrupting ratings of the overcurrent protection devices, it is also important to consider the coordination of the overcurrent protection devices. Coordination is the process of selecting overcurrent protection devices so that the device closest to the fault will operate first. This helps to minimize the extent of the outage and protect the equipment from damage. The coordination of overcurrent protection devices can be achieved by using time current curves. Time current curves show the time it takes for an overcurrent protection device to operate at different current levels. By comparing the time current curves of different overcurrent protection devices, it is possible to select devices that will coordinate properly. The upgrade from a 3-wire delta system to a 4-wire system is a significant change to the electrical system. It is important to carefully plan and execute the upgrade to ensure that it is performed safely and reliably. The utility should provide the customer with detailed information about the new system, including the transformer size, the fault current level, and the grounding system. The customer should also consult with a qualified electrical engineer to ensure that the electrical system is properly designed and installed. Regular inspections and maintenance are essential to ensure the long-term reliability of the electrical system. The electrical system should be inspected on a regular basis to identify any potential problems. Any problems that are identified should be corrected promptly. The electrical system should also be maintained in accordance with the manufacturer's recommendations. By following these guidelines, the customer can ensure that the electrical system is safe, reliable, and efficient. The information provided by the utility regarding the new fault current being around 22,000 amps at the transformer bushings is a critical piece of data for assessing the adequacy of the existing electrical infrastructure. It's important to understand that this value represents the maximum potential fault current at the specific location. The actual fault current experienced at downstream devices will be low due to the impedance of conductors, transformers, and other components in the circuit. However, this value serves as the starting point for determining whether the existing protective devices are sufficient. The existing main fusible switch with fuses rated at 300,000 amps interrupting rating is significantly higher than the 22,000 amps available fault current at the transformer bushings. This indicates that the main fuses are adequately sized to handle the maximum fault current at that location. However, the question specifically focuses on the molded case circuit breakers in the distribution panel and the high rupturing capacity fusing in the motor control center. These devices are located downstream from the main fuses and are therefore subject to a reduced fault current due to impedance. To accurately determine whether these devices are adequately rated, it is necessary to perform a fault current study that takes into account the impedance of the conductors, transformers, and other components between the transformer bushings and the devices in question. The fault current study will provide the available fault current at each point in the system, allowing for a direct comparison with the interrupting ratings of the circuit breakers and fuses. If the available fault current at any point exceeds the interrupting rating of the corresponding protective device, the device must be replaced with one that has a higher interrupting rating. It is not sufficient to simply assume that the fault current will be low enough due to impedance. A proper fault current study is essential to ensure the safety and reliability of the electrical system. In addition to checking the interrupting ratings of the protective devices, it is also important to consider the coordination of these devices. Coordination ensures that the device closest to the fault will trip first, minimizing the extent of the outage and preventing unnecessary damage to equipment. This can be achieved by selecting devices with appropriate time current characteristics that allow for selective tripping. For example, the main fuses should have a time current curve that is higher than the time current curves of the downstream circuit breakers and fuses. This will ensure that the downstream devices trip first for faults within their zones of protection, while the main fuses only trip for faults that exceed the coordination threshold. The high rupturing capacity fuses in the motor control center are designed to provide a high level of fault current protection. These fuses typically have a very fast response time and are capable of interrupting high fault currents without causing significant damage to the equipment. However, it is still important to verify that the interrupting rating of these fuses is adequate for the available fault current at their location. The National Electrical Code provides guidance on the selection and application of overcurrent protective devices. National Electrical Code Section 110.9 requires that equipment intended to interrupt current at fault levels shall have an interrupting rating sufficient for the nominal circuit voltage and the current that is available at the line terminals of the equipment. National Electrical Code Table 110.9 provides guidance on the maximum available fault current for different voltage systems. It is important to consult the National Electrical Code and other applicable standards when performing fault current studies and selecting overcurrent protective devices.